Greetings and welcome back. Today we'll be looking again at the relationship between two different molecules, and the relationship we'll be examining today is enantiomers. Enantiomers is a word that we've used already. Essentially it just describes chiral molecules that are R and S, or right-handed or left-handed. And that's really all there is to it. However, I wanted to make a short video on this so that we could kind of keep this in the vein of relationships between molecules. So, enantiomers are simply things that are stereoisomers, that is to say, they do have the same molecular formula, they do have the same bonding, that is to say, things are in the same place, except that one of them has a chiral center that is R, one of them has a chiral center that is S. Therefore, these guys have the relationship of being non-superimposable mirror images. They are enantiomers. And the enantiomers are simply non-superimposable mirror images. And this is relatively easy to figure out. You can name them, and they should have the same name, except that one of them will be R and one of them will be S. So we can do this in this instance. I don't have my hydrogens drawn in, but I can. There it is. And I can rank these guys 1, 2, 3, 4. And in this case, the number 4 is in the back. So 1 to 2 to 3 would give me R. And that molecule is R2-butanol. This guy on the right is probably fairly obvious, but we'll do it anyway. Here's number 1. We'll draw in our hydrogen. And our hydrogen is in the front in this case, so it'll be a little bit more work, but that's okay. 2 and 3. And so we can rotate this around, or we could remember the little shortcut. If number 4 is coming out at you, you do 3 to 2 to 1 for your arrow. And this would be counterclockwise, or S. So this is S2-butanol. I find that the easiest way to tell whether or not molecules are enantiomers is, well, sometimes they're just drawn out as obvious as this, one on a wedge, one on a dash, and in that case you can know that they're enantiomers. But if you can't, if they're drawn in kind of funky different ways, or you're given a name in a structure or something like that, is always just to figure out for that one chiral carbon if one's R and one is S. But wait, you might ask me. I'm waiting for you to ask that. Okay, hopefully you didn't say it too loud in public. What if we have 2 chiral carbons? Well, if we have 2 chiral carbons, I'll move all of this up, then they still need to be non-superimposable mirror images. So for instance, if you have this molecule right here, it does have 2 chiral carbons. So if we look at this chiral carbon on the left, you'll notice that we have an OH, a big old group, a CH3, and then there's an H back there. So those are 4 different things. If you look at this carbon right here, we've got a methyl group, we have a hydrogen, we've got an ethyl group, and we got that big chunk. So this one is also chiral. So this would give us 2 chiral carbons in this molecule. And the mirror image of it would have to have both of them reversed. So therefore, the mirror image of this guy would be this one. And that would be the enantiomer. So if we name this guy, we would have it as, let's number it, 1, 2, 3, 4, 5, 6. So this would be a 4-methyl-1-hexanol. But we can't just put R or S out in front because we have 2 chiral carbons. So we would need to figure them out. We already did the one on the left already. It turns out to be exactly the same. That spot right there is R. We haven't done the one on the right, so let's work through that. All right, so I'm going to draw my hydrogen out. My hydrogen is coming towards us. That is number 4. The ethyl group on the right is my number 2. The big old chunk on the left is my number 1, and the methyl group right here is number 4. I invite you to work through that on your own. If you're not exactly sure where those numbers came from, just ask me in class. And once again, if the 4 is coming out at you, we can just draw our arrow from 3 to 2 to 1. So this carbon right here is S. So the way that we would write this out would be that we have a 2R, because carbon number 2 is R, and we have a 4S, 4-methyl-1-hexanol. So the mirror image of this would have to have everything reversed, because when you look in the mirror, everything is reversed. And therefore, the mirror image would be 2S, 4R, 4-methyl-1-hexanol. And that is it for enantiomers. Enantiomers, if you recall from the very first video where we talked about chirality, enantiomers have the same melting point, they have the same color. What differs in them is the way that they rotate plane polarized light, something that we will do or have already done in lab. And so that ends up giving us a value that we denote like this, which is the rotation of light. I don't know exactly how this guy rotates light, but it would. And so if this guy rotates light at plus 14 degrees, then this guy on the right, which is its enantiomer, would rotate light at minus 14 degrees. With structural isomers, we have no idea how they're related in terms of their rotation of light. But with enantiomers, you can always tell that they're going to be equal but opposite rotations of light. And that's kind of the one way that we can tell them apart physically. All right, please practice this. But again, we've now added a second relationship to your arsenal. We have structural isomers, and now we have enantiomers. Thank you very much, and I'll see you in class.